Okay, so first let's recall what we have learned last time. We started with the derivatives and about the graph. So one thing we know that when a derivative is positive, that means the function is increasing. When the derivative is negative, function is decreasing. Okay, that's easy, very easy to say. Increasing, something like this, decreasing. Okay, let me check with you. From A to B, what can you say about the graph? Increasing. What can you say about the derivative? So be positive. Next one, B to C, decreasing, negative. Okay, very easy. So now let's look at this point B. On the left, it's increasing. On the right, it's decreasing. Right? So this point is a local maximum. So local maximum, if we have this pattern, on one side with positive derivative, the other side negative derivative, then this point will be a local maximum. Okay, a very simple criteria. Yes, something like this. Similarly, yes, the left is decreasing and on the right is increasing. We have this graph. Okay. Local maximum and local minimum, very simple. Next, we will study the second derivative. What does the second derivative tells us about the graph? Let's look at this graph. If we compare the slopes at different points, point, so this graph, it has the feature that the whole graph lies above each tangent line. You see, that for comparison, if I go with this curve, then I draw the tangent lines. On the right, the whole graph lies below this tangent line, below the tangent line, the two different behaviors. Now let's, if we, so this is the function. What can I say about the derivative? The derivative at this point will be the slope. Derivative at this point will be the slope. Which one is bigger? So this one is bigger. So for this one, the derivative is increasing. What can I say about the second derivative? Okay, this implies, so in this case, we give it a name. So in the book, it's called concave upward. Another name, maybe more popular, after you are done with calculus, is called convex. A function which is also called convex, different names. This one, what can I say about the derivative? At this point, and the derivative, derivative here, which one is bigger? The first one is bigger. But this one, the whole graph lies below the tangent line, below the tangent line. So the derivative becomes smaller. The derivative is decreasing. What can I say about the second derivative? It's negative. Sometimes we can put an equal sign. More. I will add an equal sign here. Add an equal sign. This time we call it. Okay. Oh, okay. That's what they call it in the book. So sometimes we just concave. Okay. Mm. Then let's check this function x cube. We have drawn it several times. Okay. If I look at this one, concave, convex, or neither, what can I say about this function, the graph? How do you determine which part is let's say we use convex? Okay, so this part will be convex, this part concave. What about this point? Transition point. The transition from concave to convex, so we call this an inflection point. Okay, okay, first we check f derivative to x squared. Okay, what's the second derivative? Okay. Okay, now we can see this one is a positive when x is positive, negative when x is negative. So we conclude x positive if x negative. And at this special point, so it's the transition from concave to convex called inflection point. Okay, so how the trend is changing. So this is about the second derivative itself. If we combine the first and the second derivative, we get a little bit more information. The second derivative test. This is about the critical point. Assume this is 0. Then we will divide our discussion into 3 cases according to the second derivative. Okay, so with this information only. Okay, so at this point, the derivative is 0. What can we say about the graph when the derivative is 0? The tangent line. So what can we say about the tangent line to the graph at this critical point? The slope is 0. There must be a horizontal line. Okay, so the horizontal line, the second derivative is positive. Okay. So the second derivative is positive. It tells us this function is increasing. The derivative is increasing is but we also know fc is 0. Okay, it's an increasing function. At c is 0. What can we say about f derivative if x is less than c? Positive, negative, or 0. Increasing function. At some point, it's 0. Now what happened over there? It will be less than 0. Okay. Less than c, less than 0. Can say about the derivative if x is bigger than c. Then the increasing at c is 0, at c will be positive. Okay, now let's look at the derivative. On the left, it's decreasing. On the right, it's increasing. What does this tell us about the function itself? Okay, so we have a critical point. So the graph will be something like this. One left is decreasing, and C is a critical point. Then it becomes increasing. So this time, at a critical point, if the second derivative is positive, it will be something like this. We have a local minimum. Okay, it implies. Okay, the second case, when the second derivative is negative, now we just reverse everything. Reverse everything. What can we say about the derivative in this case? Decreasing. Decreasing again is zero. What can we say about the derivative when x is less than c? So they will be positive. Positive decrease to zero. Okay. So this means combined with this information, we have the graph. So on this side, f derivative, f derivative, f derivative. Okay. The same thing we have just mentioned. When the first derivative changes from negative to positive, we have a local minimum. First derivative from positive to negative, local maxima. Okay, the remaining case. Okay, what's the remaining case? We have positive, negative. What's the remaining case? Zero. Okay, we know that the first derivative is already zero. The second is also zero. This time, we cannot tell if it's local maximum, local minimum. The conclusion is inconclusive. Oh, too much. Okay, very important case. So have to use more information. Okay, okay. So the next section we introduced the loptolity. Okay, in some books they have this spelling. The spelling some may use. Okay, so so because this is he's the French, we don't. There's no S, there's no H, law, theta. Okay, you know how to reread this. So the law theory is not about any limit, but only about indeterminate form limits. Determinate. Okay. There are several types. The first type is zero over zero. Okay, again, this is not a fraction, it's not a number, it's a type. Okay, so emphasize not a number, but a type. It means where both if the limit has this property, when the numerator and denominator, they both go to 0, then we say this is a limit of indeterminate form with type 0 over 0. Okay, a little bit long, but it's very simple. Okay, so in this case, the L'Hopital's rule tells us this these two limits, they are the same. This includes the case when both doesn't exist. If this exists, this also exists, and they have the same limit. If this one doesn't exist, this one also doesn't exist. Okay, and the first verification we have about this rule. Okay, first, what's the type of this limit? All right, okay. So, and we can apply the L'Hopital's rule. Cosine x over 1. Now we can plug in, so it will be 1 over, plug in the cosine 0 over 1. Again, this is not how we initially found the limit. We found this limit using the geometric argument. Because in this process, so this process involves the derivative of sine x. We already used this limit to find the derivative. So I have to say this is just a verification or justification. You cannot use this as the definition, as the primary rule to find the limit. Because in this process, we use the property of the derivative. And in this process, we already used this limit. Okay, but we have some other applications. Second application we had, so this one, because we know logarithm 1 is 0. When x is 1, this is 0. Again, it's the type of 0 over 0. So let me maybe write down a type. Again, it's type. So we can apply the L'Hopital rule. Okay. And the last example we had is about this limit. Do you remember this one? Okay. Okay, let's redo this. Again, so what's the type? Okay, so we can apply L'Hopital rule. Okay, I will give you a few minutes to complete this. What's the derivative of the numerator? Okay. Uh-huh. Okay. Could we plug in? So what should we do? Okay. Again, we verify the type against the type. Are you done? What's the result? Okay, nice. Okay, so sometimes we have to use this L'Hopital rule repeatedly to find the limit. And at each step, before we apply the L'Hopital rule, we have to check it has the necessary type. If it's a different type, then we stop. If we go any further, we get some contradiction. Okay, this is the first type when both go to 0. So we want to see which one goes to 0 faster, which one goes slower. The second is the type. Second type, it means we consider this limit when both is very similar to the previous one. We just replace this from 0 to infinity. Okay, if we have a limit of this type, we can apply the corresponding L'Hopital rule. Again, keep in mind, this is not the quotient rule. No, it's the quotient of the derivative. This is the L'Hopital rule. So let's start with first. Let's check this function fx equals e to the x. What happens if x go to infinity? The exponential function to go to infinity. What happens if x go to negative infinity? All right, okay, perfect. Perfect. Okay, with this, we want to find the limit. Okay, first, let's check. Is this the type we required? What happens to the numerator? What's the limit of the numerator? The denominator? Okay, so first is our type. create the type, then we can apply L'Hopital derivative of the numerator. Derivative of the denominator. Okay, what's the limit? The numerator is 1, denominator goes bigger and bigger. What's this fraction? It will go to 0 because denominator goes to infinity. Okay, nice. Now, next one, limit. X squared over e to the x. What should we do? Okay, let's L'Hopital rule. X e to the x. What's this limit? Okay, there are different choices. We could keep going because this go to infinity, this also go to infinity. This is the type infinity over infinity. Or we can compare this with the previous one. If we omit these two, they remain the same, right? Over there, we found that the limit is 0. So what's the limit of this one? Okay, nice. So we don't have to repeat, but we can apply the previous step. 2 times 0 equals 0. Okay, good. One step further. Limit x go to infinity, x cubed. Okay, let's find this limit. What would you do? Start with small steps, not the final result. Okay, so we apply L'Hopital's rule. We get, because the derivative of the exponential is itself. How do you find this limit? Repeat the process or use the previous step? Okay, so what's the limit? This will be 3 times 0. Now we have checked 3 of them. I will give you a general question. What's the limit? X to the k. That means make it more 100. Okay, how do you get that? Uh-huh. Okay. Okay, so what's the name for that proof? Uh-huh. So mathematical induction. Okay, so the name of the proof, so mathematical induction. So proof. Okay, proof by induction. Okay, so we don't have to check them one by one. We can complete the induction step. This will prove the general case. And more generally, not only for integers, for any real numbers. For any real numbers, let's say 105. What's the limit of this? 571. Okay, I'll make it more complicated. How do you find this limit? So here, if we apply the derivative, it will pass 0. So because this decimal places, but because this one can use the squeeze theorem. When x is bigger than 1, it goes to infinity. Is less than x1 or 1. If we divide it by exponential x, this one go to 0, so this one also go to 0. So in general, have the following limit. Any number. It means any real number. You can see I mentioned 100, 1,000, 1,000,000 is all the same. In this sense, so we see this exponential function as x go to infinity grows faster than any polynomial. So now you may have seen the term polynomial growth and exponential growth. So if we see something is grow exponentially, it grows much faster than this polynomial growth. Okay. Okay, so the faster ones. Okay, now let me ask you, could you give me a function that grows the fastest? No one grows faster than it. Can you give me a function that grows the faster and no other function is faster than that function? Is this exponential function? Could you give me something grow faster than this? Okay. Oh, you have another one. Okay. Yes, you give me this function. This grows faster than exponential function. Okay, can you ask me why? Uh, okay. Okay, so we want to compare this with our exponential function. Let's change them to the same basis. If we want to change it to base e, what's the new exponent? Okay, try. How do you find this exponent? So it's something, if we take logarithm of both sides, what's this? There will be the exponent, right? What's logarithm of this? Yes, so that's the exponent. Okay, so now you figured out. So next time, I cannot accept the no. Have to tell me what it is. So we want to compare these two functions. Now, so this function grows faster than this one because we have additional factor that goes to infinity. So this will grow faster than exponential. Can you make something grow faster than this? If I put exponential of this, it will go faster. What if I put x, this, I could put another one, I put another one. So there's no, the fastest growing function. You can always make it faster. Okay, that's the point. Okay, now with the faster one, I'll go to the slower one. Uh, this logarithm function. This logarithm function. It goes to infinity, but we can see the slope becomes smaller and smaller. Okay, what's the derivative of logarithm? Okay, nice. So here we can also see when x increases, the slope becomes smaller and smaller. So the growth slower and slower. How slow? Let's compare these two functions. X go to infinity. Logarithm x square root of x. Okay, when x go to infinity, this go to infinity, this go to infinity. Which one go to infinity slower? What's your guess? Okay, so how do you find this limit? Okay, L'Hopital, derivative of the numerator, derivative denominator. Okay, can you simplify this? So to make this simpler, I'm going to move this to the front to simplify the fraction. It's 1 over x time 1/2. Is that right? So 1 over x move to there and copy the rest. Okay, so this is limit infinity to over x 1/2. What's this limit? Numerator constant. Denominator goes bigger and bigger. 0. Now the limit is 0. So which one go to infinity slower? The top one. Okay, so this one is slower than the square root. That's a cubic root. Okay, I will give a minute to figure this one. We'll compare it with cubic root. I want to see which one is slower. Let's try. Okay, what's the first step? Okay, what's the numerator? Denominator? How do you simplify this? Okay, what's this limit? 0. Okay, now which one go to infinitely slower? Okay, now, so without any computation, can you guess what's this limit if I replace 100? So 100 square root, it goes to infinity very slow. Which one is slower? Okay, how do you verify this? No, no, this time it's not induction. This time you apply L'Hopital rule. Okay, you go ahead. So the difference, sometimes you say, okay, induction, but this time we cannot use induction. It doesn't work. What do you get? 0. Okay. Okay, so now we have the general formula and we don't have to use induction. For any positive number, no matter how small it is, as long as it's positive, this limit will be 0. That means the logarithm function grows much slower than even a tiny bit of positive power. Okay, could you give me a function that grows even slower than this? If this is the slowest, so as this function goes to infinity very slow, could you give me something that is slower than this? Log of log. Okay, so we make it slower. Log, 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 go to 0. Okay, slower. Again, we can if we repeat this. So now let's see what our polynomials. So have x, it goes, this is slower than x squared, slower than x cubed, slower than exponential, slower than x. So there are many functions slower, but it's faster than square root, faster than cubic root, faster than logarithm, faster than. So we have a chain, maybe even it's a chain of functions. They all go to infinity, but at a different speed. There's one linear, square, cubic, exponential, super exponential. Logarithm, I'm not sure. That maybe repeated logarithm or double logarithm. And something in between is maybe a little bit of brain twister. Logarithm x square over x. What's this limit? Could you do it without any computation? We have a square. How do we deal with square? Yeah, okay, that's the criteria. So we square is logarithm times logarithm. And this square root is 1/4 root, 1/4 root. Each of this go to 0. the product also goes to 0. Okay, just a sketch. Limit x goes to infinity. Logarithm. 1/4. Do you agree? Okay, because both go to 0. And see, not only the logarithm square is slightly faster than this, but slower than any of this. Okay. Again, we have to check if it's the right type, we will apply L'Hopital rule. If it's not the type, we do not apply L'Hopital rule. Okay. Next, we will generalize, give some generalizations of the L'Hopital rule. We can apply it to more general case. So, indeterminate type. Let's have 5 minutes break. We'll be back at 58. Okay. Okay, so the third type. The previous two types, what are they? Okay, so 0/0, type 1, infinity over infinity, type 2. The third type is about the product. Again, it's not a real product, it's a type. Okay, it means we want to find the following limit. The product where one of them so one of them go to 0, the other go to infinity. So we want to see the competition, which one wins. If this go to 0 much faster, then the overall will be 0. If it goes to infinity much faster, the overall will be infinity. So who wins? Or maybe there's a balance, we get a number. So to find the limit, we will convert this limit type 0 times infinity to one of the previous two types. Sometimes we converted it to this type if it's easier. If not, we convert to this type. Okay, have a choice. Approach. Okay, let's try one. The limit x go to 0. Okay, let's check. When x go to 0 for positive number on one side, what's the limit of this logarithm x? Logarithm x, when x decreases to 0. So it means we approach the limit from, yes. Okay. So this one, we know when x approaches 0, it goes negative infinity. If you look at the graph we had before, so you can see when it approaches this 0, it drop deeply. Okay, it goes negative infinity. So this it will be 0 times infinity. Now to find the limit, we will convert this. So how do we convert this? It's converted to fx quotient. How do you convert this product to a quotient? The reciprocal is 1 over gx, or 1 over fx gx. Oh, sorry. It's not what I meant it. Is it 1 over fx gx, 1 over fx. So for this one, 0 over 0. This one, infinity over infinity. Which one do you want to try first? 0 over 0 or infinity over infinity? Okay, let's try this. So 0 over 0, let's try. What will be on the denominator? But so this time, if we take the derivative of this, easy, but derivative of this become much more complicated. So instead, we will, so this one seems complicated, so we switch to the second type. We want to try limit infinity over infinity. Okay, what's the new denominator? Over x. Still complicated, but seems manageable. Okay, let's apply the L'Hopital's rule. Derivative of logarithm, what's that? 1 over x. Derivative of 1 over x. So it's x negative 1 derivative. We will subtract 1. Subtract 1. We simplify. Okay, how do we simplify this? Numerator 1 over x. Denominator negative x negative square. So we put this, the denominator, we get x. We put this on the numerator, negative x squared. We get negative x squared x. Okay, so we find this limit. So this is 0. Now let's think about this one. Limit x go to 0. Okay, if we finish, because when we deal with this complicated formula, the exponent can be fractions. The base must be positive. So I will put a positive sign over there. How do you find this limit? So this is a new type. This is a type 0 over 0. So more generally, fx, gx with both So this time should be very careful. Even though it's 0, there is allowed on the base, 0 is allowed on the exponent, but we cannot have both. If we approach this on different direction, we get different limits. So what does that mean? Let's see, two different cases. Limit x to the 0. What's this? Okay, because x0 is always 1. When x is positive, limit x is equal to 0. 0x, what's this limit? 0 to the positive power is still 0. Now if we look at this too, what's the limit of this one? Is it close to this or is it close to this? What do you guess about this limit? If this one dominates, should it be 1 or should it be 0? Or should it be something in between? Okay, so it's not easy to tell. We have to use some more accurate method. So for this one, we use we have used it several times. We change this to the exponential basis, change of basis. If you change of basis, okay, what's the new exponent? Okay, nice. Now you get this. Gx fx. Okay, so if we can find this limit, then we take exponential, we get this limit. So in order to find this time, this go to 0, this go to infinity, 0 to infinity will reduce this type to the previous type. Okay, so as an example, we're going to go back to find this one. What's the limit of the logarithm? X to the x, what's the new exponent? Change of basis. X log x. What's the limit when x goes to 0? We just found over there. 0. Now, what's this limit? Nice. X with 0 plus. This will be the limit. E to the x logarithm x to 0. Now we can see this limit is 1. Okay. Another type. Infinity minus infinity. Again, not the difference of two infinities, but a type. Type Let's see through an example. For clarity, I consider one secant x, tangent x. Okay, first let's recall when x goes to pi over 2. What does this mean? Okay, maybe I should ask you first. Okay, yes. It goes to pi over 2. This is pi over 2. X goes from there, from the left side. When x goes pi over 2 from left side, what can you tell me about the tangent x? What's the graph of tangent x? So when x approaches the pi over 2 from this side, tangent x goes to infinity. So this goes to infinity. What about secant? So what's the definition of secant? The 1 over arc over cosine x. So cosine x is like this. So it's decreased to 0. So this again will go to positive infinity. Hmm? So because cosine x will decrease to 0, so go to 0 on the positive side. So this implies secant is 1 over cosine x. It will go to 1 over 0 if it goes to infinity. Mhm. How do we find this limit? They both go to infinity. Is there a tiny difference between the speed of them? Okay, it's not easy to tell. What we do, we will use a definition. Secant is 1 over cosine. What's tangent? Sine over cosine. Okay, we want to put this common denominator. What do you have? Now, what do you say about the denominator? Numerator, y minus sine pi over 2. Again, it's 0. So it's the type. Okay, what should we do from here? L'Hopital rule. Derivative is correct, but the L'Hopital rule make it more clear what we are doing. Okay, so what's this limit? Okay, okay. Okay, so this, when you see infinity over infinity, we cannot plug in because we don't know how to evaluate this. So what we can do is we can somehow convert this to the type of 0 over 0. Then we apply L'Hopital rule, we get the limit. Okay, a few more limits. Limit x go to infinity. Okay, we mentioned it before. X goes to infinity faster than logarithm. What's the limit of the difference? Okay, so what do we do? Okay, when we unlike the previous one use the definition, we convert it to a fraction very easily. So here there's no natural convection. So we'll make up one. We pull out x. Okay, so what's the type of this limit? It's zero? What's the limit of this? Okay, so let's try to recall what's the limit. Okay, you want to apply L'Hopital rule. You want to apply L'Hopital rule 1 over x 1, and this is 0. So now, what's the limit of this one? So it's now it's infinity times 1. We don't have to do anything. Infinity times 1 is infinity. Okay, it's not a L'Hopital rule. This time, x goes to 0 much faster than logarithm. Okay. Uh, okay. Let's try. So how many types have we learned? A summary. Two basic types. Two basic types. These two we can apply L'Hopital rule directly. Then a slightly more general one. If it's the product, one go to 0, one go to infinity, we try to convert this. 0 over 0, or infinity over infinity. We want to see which one is easier, and we can apply L'Hopital rule. Another type, uh, infinity minus infinity. Again, we want to convert this to a fraction. To the product, okay. And the last time we have this powers, this quotient. This is product. And difference. And then we have this power. Power, we have 0, 0. There are other types. It's 1 times infinity, infinity times 0, 0. Okay, what does this to me? So this one we have one example we have discussed before. For this one, consider the following limit. When x go to infinity, 1 plus 1 over x, the power of x. I think we have seen this before, but I want to check. Can you see this? Do you have some vague memory of this one? Okay. How do we find this limit? How do we find this one? Chain of bases. Whenever we have a power, we apply chain of bases. Let's apply this chain of bases. Okay, what's the new exponent? Okay, now what's this limit? Mm, Is it similar to what we have done before? Mm, Okay, maybe it's slightly different. So let's try, how do we find this? What's the type? Let's go to infinite. What about this? This goes to 1. Logarithm 1 is 0. So this is the type. So for the product, how do you find the limit? Okay, nice. Yes. So we will convert it to a fraction. Logarithm seems complicated. Seems complicated. Okay, then we apply L'Hopital's rule. So it's derivative of the numerator by a chain rule. Derivative of the denominator. All right. They cancel each other. Only this left. Okay, so what's this limit? X to infinity. 1 over x is then the 1 plus 0, 1 over this 1. Now what's this limit? The exponent goes to 1. What about this? Limit x go to infinity. Let me copy the formula. X logarithm. So this thing goes to 1. Okay, so this can be viewed as the definition. How do we compute this E? We find the limit from here. We make X bigger and then bigger. We find the power. Let's see, if X is 100, it will be 101 to the 100th power. This will be a very good approximation of E. If you go to 1,000, a better approximation, 1 million, maybe even better. That's how we find this number. Okay, so we will stop here and we'll have a brief review of this L'Hopital rule next time. I will make sure you remember this. Okay,